Okay, we're continuing on here. We've been talking about stoichiometry and doing stoichiometry problems, which are really calculations from the balanced equation. Pretty much as we talked about, there are four basic steps to these type of problems. Pretty much none of this stoichiometry works if you do not have the balanced equation. So that is always really the first thing that you want to do. You want to just make sure that if you are given the equation and that it is balanced. Obviously, if it's not, then that is definitely the first thing that you want to do. The second thing you want to do is really take whatever they give you and sort of take what they give you and convert it to moles. And the most sort of common way to do that is a lot of times you're given things in grams and you'll need to convert them to moles. Remember that it is the molar mass from the periodic table that allows you to do that. When you go to the periodic table, the molar mass is the number on the bottom, and you just add up all the parts that are there. And the units of molar mass are grams per mole, which you can use as a conversion factor. Again, the number stays with the grams part. It's always 1 mole. And another important thing that we talked about last time was regardless of what the coefficient is, say in the balance equation, whenever you are calculating molar mass, it is based on just the formula by itself. And that's why it's per mole. So regardless if in the equation there's like a 4 in front of it or something like that, it has no effect on when you calculate the molar mass. You just do it based on the formula. Once you have that, the whole point of this calculation is really the third step here, which is the stoichiometry calculation. And that is because probably whatever they gave you in the actual problem is not what you're interested in. You're interested in somebody else in the equation. So that is where we use our mole to mole relationship from the balanced equation. So if we had, A2 plus B2 goes to AB2, and we had we got moles of AB, but we wanted to really know about moles, say, of A2. There's just the coefficients, that relationship. So from this equation here, that would say for every 1 mole of A2, you get 2 moles of AB. Remember, that gives you basically 2 conversion factors that you could use, and they're just like any other conversion factors, fractions, basically. Or you could flip it around the other way, depending on whichever way you need to use it. So once you do that, that's going to allow you basically to do the stoichiometry part of the calculation. And at that point, you should, when you get to say step 4, you should always be in the units of moles. So if you are not in the units of moles at this point, you definitely did something wrong. You should always be at moles at this particular point. The last thing that you do in these type of problems is it depends on what the problem is asking for. If it's asking for moles, you pretty much could put a box on it and you should be done. But very commonly, they want some other unit as sort of the answer. And very commonly, you are on the back end of this calculation going from moles back to grams. And once again, that's going to be your molar mass conversion from the periodic table that's going to allow you basically to do that. So it really is, again, no matter how kind of crazy the problem may look or seem, if it's a basic stoichiometry problem, it really is just these 4 steps. You want to always kind of go in order. And if something's done for you, then you want to go to the next step. So any questions on the stuff we did last time there? All right, so let's take a look at a couple more examples here. So why don't you give this a go? We have this equation here, and we are reacting 765 grams of C6H12O6, and we want to know how many grams of CO2 will be produced in this case. Let me give you some info that might be helpful. Carbon is 12.01. Hydrogen is 1.008. And oxygen is 16. All right, so take a few moments. Again, follow those 4 steps and see if you can figure out how many grams of CO2 we should produce in this case. Yes. Do I have any? I have, they have this, that work? Yeah. Okay, yeah. Yeah, you're right. Yeah. Let's take a look, see how you're doing. So again, we want to follow those steps. So first step here is we want a balanced equation, and I see coefficients. So I feel pretty confident it's balanced. And if we do look at it, it is balanced for sure. In this case, we're given 765 grams of this guy, and we're not really interested in that guy. We eventually want to get over to the CO2. And that essentially means that this is a stoichiometry problem. That's really the whole purpose of it. Really, stoichiometry is just a conversion factor. And again, instead of looking it up in a table, you basically get that conversion factor from the actual equation. So before we could do that, we do have to get sort of the number they gave us into the right units. And that is the second step, which is whatever they give us, we want to convert to moles. And we do need to do that in this case since we're given it in grams. So we do need to take these grams to moles. Once again, that is the molar mass from the periodic table that's going to allow us to do that. So we basically just need to add up all the parts for this guy right here. So that is 6 times 12.01 for the carbons, plus 12 times 1.008 for our hydrogens, plus 6 times 16 for all the oxygens that are present. And if we do all that, remember when you take the molar mass off the periodic table, it is typically 4 significant figures that you take it to. And if you add all that stuff up correctly, would be good, I suppose. Looks like you get 180.2 grams per mole. And again, that is the molar mass here of our C6H12O6 here. So we're going to use that as our conversion factor. And again, obviously, we got all those numbers from the periodic table. So step number 2, we'll take the 765 grams that they gave us of C6H12O6. We're going to use the molar mass as a conversion factor. So remember, opposites cancel. That means that we do need the grams on the bottom. That's a 12, I suppose. A 12. There we go. And up on top would be a mole of C6H12O6. Those grams are going to cancel. And again, if you get an answer at this point, which you don't necessarily have to, but if you did, once again, I probably would not round too much at this point, but you would get 4.24528 moles of C6H12O6. So we're basically just converting our grams into moles. The purpose of that is it needs to be in moles for really the next step to work. So that's really the whole purpose here of the second step, is just to get everything into the right units. Any questions on that so far? Now where you got it, hopefully in the right units, we're ready to do really the third step here, which is the stoichiometry step, and that's that mole to mole relationship. And that comes from the balanced equation. So in this case, the one thing that we're interested in is what they gave us, which was this guy. The other thing that we're interested in is what we're trying to find, which is this guy. And remember that the stoichiometry relationship is nothing more than just the coefficients. So those tell you how many moles you have of that. So the coefficient on the first guy there is 1. So that would be 1 mole of C6H12O6 would equal coefficient on the CO2 is a 6. And that would be 6 moles of CO2. That is the stoichiometry relationship from the coefficients. That again gives us really the conversion factors, which is really all we're looking to use this for. And that gives us 2 conversion factors that we could use. And like normal conversion factors, we will only use one of them, not both. And again, we're going to use the one that we need, which is the opposite of where we're at. So continuing on with our number from above, we have 4.24528 moles of C6H12O6. Once again, opposite's going to cancel, which means we will need to use a conversion factor on the right there so that they cancel. That's going to give us 6 moles of CO2 and 1 mole of our C6H12O6. Those moles are going to cancel. So we're basically just going to multiply this by 6, and that's going to give us 25.4717 moles of CO2. Any questions on the stoichiometry part there? Again, if the question was how many moles, I would actually be done. I just want to round to the right number. But in this case, we're not looking for moles. We are looking for grams, which means we do need to do the fourth step, which is convert our moles, in this case, to grams. So we do have to remember that we have now sort of transitioned to CO2. So to convert to grams of CO2, I once again need to go back to the periodic table and get the molar mass of CO2 and use that as a conversion factor. So CO2 from the periodic table, 1 carbon at 12.01 plus 2 oxygens at 16. And that's going to give me 4401 grams per mole. And again, that is the molar mass of CO2, which we're really just going to use as a conversion factor. So continuing with our number from the previous step, 25.4717 moles of CO2. Here we do want the moles to cancel, so the moles will go on the bottom. The grams will go up on top. And that will get us here about 1,121 grams of CO2. At this point, we could kind of clean it up significant figure-wise. Really, this is the only number that was given to us, which is 3 significant figures. So probably this should end up at about 1,120 grams of CO2 would be produced in this case. That is what is known as the theoretical yield. If everything went perfectly, basically what that number means is if you put into that reaction 765 grams of C6H12O6 and everything went perfect, you should get out of that equation or reaction about 1,120 grams of CO2 should be produced. Again, it is the same 4 steps. As I mentioned last time, you could do all the calculations together. You don't have to kind of get answers in between if you don't want to, or if you want to get answers in between, you could do that. Just make sure, again, if you are doing the answers in between, you kind of don't round too much until the end. Any questions on any of them there? All right, let's try another one here. Let's try this one here. How many grams of cisplatin, which is this guy, who has a molar mass from the periodic table of 300.1 grams per mole, can be obtained if you started with 0.7752 grams of this guy. Molar mass from the periodic table, 415.1 for that guy. So they're nice enough to calculate that for you, so you don't have to calculate it. So here we're looking for basically how many grams of this guy if we started with this many grams of that guy. All right, so again, follow the same 4 steps, see what you come up with here. Take a look. So even though some of these formulas may look a little scarier, it really is still the same 4 steps here. We're going to start once again with our balance equation, which again, probably if you see coefficients, it's going to probably be balanced, but you should just take a peek and make sure it is. And if you do, you should see that it is. Once again, we're pretty much starting with this amount of this guy, and we're looking for how many grams of this guy here. So step number 2 is to basically get our value into moles, and we do need to do that. So normally here we would need to go to the periodic table and look up the molar mass or calculate the molar mass for this guy, but they were nice enough to actually do that for us and give us that number, which is here. So again, that is taken from the periodic table by getting the molar mass of potassium, platinum, and chlorine and adding up all the parts. So we're going to use that as a conversion factor. So we'll start with step number 2, which is 0.775 2 grams of K2PtCl4. Once again, because they gave it to us, we don't have to calculate it, but we do want grams to cancel, so we're going to put it on the bottom here. And that's moles of our K2PtCl4. And again, that comes from the periodic table, again, looking up all the parts. The grams here will cancel, and that will get us, if you did get an answer, 0.7752 divided by 415.1. Again, not going to round too much here, so take it to a few digits. Moles of K2PtCl4. At this point, we now have really, and the purpose of this step is just to set up step number 3. Now we have everybody in the right units. We can now do the actual stoichiometry part, which is the mole-to-mole relationship. We are interested in this guy, and we can see from the equation they both have a coefficient of 1. That means that the relationship is for every 1 mole of the K2PtCl4, you get 1 mole of our product here. And again, that is the stoichiometry part, and that is the conversion factor that we're going to use. So we'll continue with our number from above, 0.0018675 moles of K2PtCl4. Again, opposites cancel, so we do want to go opposite here. So we're going to put this guy on the bottom. So 1 mole of K2PtCl4 gives me 1 mole of our guy we're actually looking for in this problem. The moles of this will cancel. Since this is a 1-to-1 relationship, I think I could do the math there. 0.001867 moles of our product in this particular case. And that is the sort of big stoichiometry step there. Any questions on that there? Now, yeah. Mm-hmm. No, it will not. It just happens to be in this. It depends where they are in the equation. So you just want to always look for basically the simple sort of way to figure out which ones you should look for is pretty much they're going to always give you a number to start the problem. Like in this case, they gave us how many grams of the first guy that's there. And the second thing that you want to look for is whatever you're really trying to find, what the sort of final answer in the equation should be. And those are always the two things that you should look for. They won't always be positioned in the first spot on each side. So yeah. Other questions? Okay, so obviously here, if we were looking for moles, we would be done, but we're not. So we are looking for grams. So we do need to do the 4th step, which is now take these moles to grams. Once again here, I will need the molar mass from the periodic table to do that. I also need to remember that I have now transitioned to this guy. And once again, they were nice enough to give us that number. If they did not, you would need to go to the periodic table and basically calculate it yourself and based on what's there. So the 4th step here, we'll continue with our number and using the molar mass that was calculated for us in the problem. We will use that as a conversion factor. In this case, we want the moles to cancel. So the moles of this guy needs to go on the bottom. And the grams, which is 300.1 grams, need to go on top. The moles will cancel. So we're basically going to multiply this by 300.1, looks like. And we will end up now with something that we could maybe round up here to 0.5604 grams of this guy would be produced in this case. This particular reaction. Again, the same 4 steps. You just want to follow it in that order, basically, and it should lead you to the end. Any questions on that particular one there? questions on stoichiometry? Yes. So we're just doing basic stoichiometry problems, which, like I said, is pretty much always those 4 steps. Just, again, if something's done for you, go forward, don't go backwards. Any questions on any of that there? All right, that wraps up then this, and I believe this will be the last chapter that will be included on exam 2, if I'm not mistaken. So this will be the last one. So I think it's 6, 7, and 8 for exam 2 coming up couple weeks, I think, if I'm not mistaken, in that ballpark. All right, so gases here. Obviously, we're going to talk about the state of matter where things are flying around. And as they're flying around, they're causing collisions. These collisions have a direct relationship on pressure. So as we have more collisions, they go up. We typically see the pressure go up as a result of that, and vice versa. Obviously, if the collisions go down, then we see a drop in the pressure. So let's talk a little bit about substances that exist as gases under normal conditions. When we talk about normal conditions, this is kind of everyday room temperature type conditions, and that is a pressure of 1 atmosphere, which is an ATM, and a temperature about 25 degrees Celsius. So under normal sort of room temperature conditions, ionic compounds typically will not exist as gases. And that is because they are held together by probably one of the strongest attractive forces, which is the opposites attract, the positive and negative attraction from those charges. So what typically would happen with an ionic compound is you could heat the heck out of it, and pretty much it will just start to melt first before it will even try to get into the gas phase. And it just really will never probably get into the gas phase at all. It will just, like I said, just start to melt before it will jump into the gas phase. Now, the behavior of molecular compounds, which are guys that share electrons, are a little bit different. There are certain compounds that are just gases straight up, like carbon monoxide, carbon dioxide, hydrogen chloride gas, ammonia, which is NH3, and methane. Those are all gases. The difference is, though, a good majority, though, of molecular compounds, which again are these guys that have covalent bonds, they typically are liquids, are solids at room temperature. But one of the major sort of differences between a molecular compound and an ionic compound is it is much, much easier to turn a molecular compound into a gas than an ionic compound. And the nice, easy example is this thing right here. Not this pipe, but it is water. Yes. So we could boil water pretty easily, and water will turn into steam, which is the gas phase of water. So we could very easily turn something like water, which actually shares electrons. So when we have something like water, water is a polar compound where oxygen is more negative, hydrogen is more positive. And when water molecules get together, they're actually held together by opposite attraction between water molecules. The negative side of one is attracted to the positive side of another. That is what is known in the case of water as being hydrogen bonded, or hydrogen bonding happening. And that is what is referred to as an intermolecular force. And an intermolecular force is a force that holds one molecule together with another. And it could be the 2 of the same molecules, it could be 2 different molecules, but it is the force that holds basically how one molecule will interact with another. And that is different than what we have if we just looked at one water molecule. The covalent bond between the oxygen and hydrogen, where they're sharing electrons, that's what's known as an intramolecular force. And an intramolecular force basically is the bonds that hold one molecule together so don't fall apart. And in the case of water, that is the sharing of electrons between the oxygen and hydrogen on each side there that holds that one particular molecule together. Now, intermolecular forces are always much weaker than intramolecular forces. And we know that because, again, when we heat water, the first bond that breaks is the bond between these 2 water molecules. And that allows this water molecule to go off into the gas phase. allows this water molecule basically to go off into the gas phase. If it was opposite and you heated water and the intramolecular bond was weaker, every single water molecule would break apart between the hydrogen and the oxygen, and you would create hydrogen gas and oxygen gas, which does not happen. And a simple example is that if you boiled water before, you could get to like the pasta making part of it. Otherwise, if you produce hydrogen gas and oxygen gas while you're boiling water, you would never get to the making food part of it because it would probably explode. So we don't separate or break water by just simply boiling it or stuff like that, but we can break that intermolecular force much, much easier. And that's also why ionic compounds pretty much do not go into the gas phase, because that electrostatic attraction, that positive negative attraction, is this one of the strongest intramolecular forces you could have, and it's just not gonna, you're not gonna be able to basically break it apart into the gas phase. So the general rule is the stronger the attraction between molecules, the less likely it will exist as a gas under ordinary conditions. That's why something like methane is a gas that comes out of that right there under normal conditions, because it's held together, one methane molecule and another one, by like a super weak force. Like you sneeze at it or just look at it wrong, and it's enough to just make it kind of go away, and they won't hold together very strongly. And that's why they are gases. That's why a lot of organic molecules, which are nonpolar, are gases. Things like propane that you might be used to, butane, methane. These are all gases, and that's because they're held together by very, very weak forces. So when you have two of those molecules together, it doesn't take a lot for them basically to separate off and go into the gas phase and make a gas. Now, substances that are found as gases under normal conditions, we have our hydrogen, nitrogen, and fluorine and chlorine. Those are our diatomic molecules, which are our elements. They are also gases, how they naturally exist. Ozone, which is O3, is also a gas. And obviously on our periodic table, group 8, which is our noble gases, those are also gases. Noble gases are monoatomic gases, which means they come as ones. And again, hydrogen, nitrogen, oxygen, fluorine, and chlorine comes as twos, which are diatomic. So here's the kind of shaded guys are the ones that are in normal conditions would be found as a gas. This is a good time to talk about the difference between two words, which is a gas and a vapor. A gas is a substance that under normal conditions would actually be a gas or be a gas under those conditions. A vapor, on the other hand, is something that normally exists under normal conditions as like a liquid or a solid, for example. So again, back to water is an example of that. Water normally exists as a liquid under normal conditions. So when we turn it into a gas, we call it water vapor a lot of times because of that, not water gas, because it sounds funny. But we call it water vapor or steam. And okay, so we're going to continue on here, and let's get into gases a little bit. One of the important sort of properties of a gas is pressure, and pressure is the main property of gases. And one instrument that's used to measure pressure is a barometer, and a barometer, traditional barometer, is used to be a pool of mercury, and it used to have like a glass tube in there. And basically, as the atmospheric pressure would apply down to the mercury in the tube would rise. Nowadays, a lot of schools are taking them out because it has mercury in it, but maybe there's still a barometer hanging around somewhere. Some of the important units of pressure is an atmosphere, 1 atm. 1 torr or a millimeter mercury are two other common units of it. A torr is named after the guy who invented the barometer. And a millimeter mercury is because, again, on a barometer, there's also used to be like a ruler, and you would measure where the mercury was in the tube with a ruler in millimeters of mercury. Centimeters of mercury are inches of mercury. So millimeters of mercury is a very common sort of unit. A torr and a millimeter of mercury are basically a one-to-one conversion. So if you need to convert between those units, you basically just change the units. The number stays the same. The relationship between atmospheres, millimeters of mercury, and a torr. 1 atmosphere is 760 millimeters of mercury, and that equals 760 torr. That means that if you have atmospheres and you want millimeters of mercury or torr, you're going to multiply by the 760 number. That will cancel out the atmospheres, and that will give you millimeters of mercury or torr. And if you have millimeters of mercury or torr and you want atmospheres, you're going to divide by the 760. And that will get you atmospheres in terms of the unit. So that 760 number is kind of an important number. It allows you to do the conversion between the different units. And again, either multiply or divide, depending on which way you are going there. Any questions? There's obviously other units of pressure that we don't deal too much with in this class, like PSI is pounds per square inch. There's also bar, which is pretty close to an atmosphere, like 1.01 to 1. So those are some other units, kilopascals, pascals. But for here, those are the big three units: atmospheres, millimeters of mercury, and torr. There's a much prettier picture of the barometer. Again, atmospheric pressure coming down on the mercury, mercury rising, hence the name. You sometimes heard that. By the way, mercury has an unusual meniscus. It actually goes the other way. It goes upwards, downwards. Meniscus, and you would reach from the top of the meniscus there. So we're going to talk about gas laws now. And when we talk about gas laws, there really is and the first gas law we're going to look at is Boyles Law. And Boyle dealt with pressure and volume, and he kept temperature constant in this case. And what Boyle saw was a relationship of this. If you have gases in a really small volume or a small volume, that means that all your gas molecules are pretty close to each other. That means there's probably going to be a lot of collisions. People are going to start banging into each other and banging into the container. And because of that small volume, we would see an increase in the collisions, and that should also show us an increase in the pressure. So as the pressure goes up, the volume goes down, basically. It's the opposite sort of relationship here. Opposite to that is as the volume goes up, you have a little bit bigger of a volume. Your gas molecules are now going to be spread out a little bit more. It's going to take longer for collisions to occur. And what we typically will see is the pressure actually will go down when the volume goes up. So the relationship that Boyle saw was basically as one goes up, the other goes down, basically, in that case. And we could basically relate Boyle's law with this equation that we see on the bottom. Another interesting aspect of Boyle's law is if you keep the temperature constant and you do any type of pressure or volume measurements and you multiply them together, you always get the same number. So if you did a bunch of pressure volume measurements under same temperature and you multiply the pressure and volume numbers after each measurement together, you'll always get the same number. So it's sometimes referred to as a proportionality constant. But what that allows you to do is actually come up with an equation like this, which is Boyle's law. It is P1 V1 equals P2 V2. This is kind of like before conditions, after conditions. The pressure here does not matter in terms of units. It could be any unit you like. The only thing that matters is it needs to be the same unit on both sides. Otherwise, they will not cancel. So if you have like an atmosphere and a millimeters of mercury, you got to get them both into whichever one you choose. Both into atmospheres, both into millimeters of mercury before you go into the equation. Same thing with the volume. It could be any volume you like. It could be milliliters. It could be liters. But again, it does need to be the same volume on both sides in terms of the units. So everything cancels. So again, there's kind of no restrictions on the units here. One goes up, one goes down in terms of the relationship. And that's what we see here at a small volume, a much higher pressure. And at a much larger volume, our pressure, which is over here, is much, much smaller. So that is your Boyle's Law of relationship. All right, so why don't you give it a go here? An inflated balloon has a volume of 0.55 liters at sea level, which is 1 atmosphere. It rises to 6.5 kilometers, where it has a pressure of 0.4 atmospheres. Assuming that the temperature remains constant, what is the final volume of the balloon? Take a moment, see what you come up with here. At this point, pretty simple to choose the right one. Kind of a good idea to pull out the information and label what it is, because very often it will kind of show you almost like the gas law that you should use. Here we do have a volume that is 0.55 liters. It goes with 1 atmosphere, which is a pressure. It rises to 6.5 kilometers, which is not useful at all, really, in this problem. We have another pressure of 0.4 atmospheres, and we are looking for a final volume here. So again, if you kind of look at it there, you can kind of see Boyle's law in front of you, and it kind of will point you. Doesn't matter which ones you make 1 and 2. So typically speaking, just in the way it's ordered in the problem is kind of what we call ones and twos. So call those guys ones, this side twos. Now, one of the things in terms of these gas laws and rearranging the equations, remember that when you cross over, uh, everybody ends in the opposite location of where they started. So what I mean by that is here we are looking for V2. And although this is not really written as a fraction, those guys are considered to be on top of the fraction. So I need to move P2 to the other side. It ends up in the opposite location. Instead of being on top, it'll end up on the bottom. And that will give me P1 V1 divided by P2 equals V2. We're essentially dividing both sides by P2. It ends up in the opposite location, basically, in that case. So that's a quick way to arrange some of these gas law problems. If you need to move something to the other side of the equal sign, it will just end up in the opposite location of where it was at. If it was on top, it'll end up on the bottom. If it was on the bottom, it'll end up on top. So it's a quick way you can kind of rearrange the equation. So now I want to plug in our numbers here. We do want to check units here, atmospheres and atmospheres. So both of our pressures are good. So we'll go with 1 atmosphere on top times our 0.55 liters divided by our 0.040 atmospheres. Atmospheres on top and bottom will cancel. That's going to leave us a volume that's in liters based off of that unit. And that's basically 0.55 divided by 0.4 gives us a 1.4 liters in this particular case. First off, any questions on that there? Now we could also, since we understand the relationship of Boyle's law, see if it makes sense our answer. Here the pressure went from 1 atmosphere to 0.4. So my pressure went down, which means my volume should go up. Started at 0.55 liters, ended at 1.4. So that's good, right? So sometimes a good idea to check just that doesn't make sense. So make sure you didn't invert some numbers, which is very common errors when you're using gas laws. Any questions on that there? Yeah. You do get 1.375 on your calculator. Here's significant figure wise. Everything here is basically 2 sig figs. Yeah. So based on just the normal rules, we would end up at 2. Yeah. What I was saying is it doesn't matter which ones you call like the ones and the twos, as long as you keep obviously the information that goes together. So for example, I called 0.55 liters and 1 atmosphere like P1 and V1. I could have called that P2 and V2. It wouldn't matter for that reason. But you do have to keep, obviously, whatever information that goes together. But it doesn't really matter if you call like them ones or twos, as long as whichever information goes together stays together. Honestly, the best rule of thumb for these type of problems is just to kind of label them in the order it is in the problem. So whatever kind of values come to first is typically what people will call like the ones, and whatever comes second is typically what people will call this too. So just going in the order of the problem is probably the easiest way not to have to worry about it. Something like that. Other questions? Okay. All right, the next law we're going to talk about is our friend Charles' law. And Charles' law dealt with volume and temperature and held pressure constant. And that is Charles' law there on the bottom there. V1 over T1 equals V2 over T2. So what happens in this situation is when we have volume and temperature, if I were to raise the temperature of my gas molecules, right? Let's say in this container, gas molecules fly around faster or slower if I raise the temperature? They would go faster, right? Like lighting a match under you, that old saying, right? You'll move faster, right? So these gas molecules would start to fly around faster. And if that volume, for example, doesn't move, that should then start to increase the number of collisions that you would have. But that is not good, because that would also cause a rise in pressure if the volume didn't move and you had a lot more collisions. So because this is at constant pressure, what happens when you raise the temperature is it will actually cause the volume to go up. And by causing the volume to go up, what happens is it gives those gas molecules a lot more room to fly around in. Even though they're moving faster, they now have a greater area to fly around in. And that's going to keep the number of collisions pretty much the same as it was previously. And that's how it's able to keep the pressure constant, is by the volume adjusting when we raise the temperature. So what we see is as the temperature goes up, we will see the volume sort of go up as well. Opposite would be true if we had some gas molecules here and we lowered the temperature. When we lower the temperature, the gas molecules are going to fly around a lot slower, which means it's going to have a lot less collisions. So that's going to cause the pressure actually to change. And we do not want the pressure to change. So what happens in that situation is, once again, the volume actually adjusts to a smaller volume, which means that although they are flying around slower, there's still going to be the same number of collisions, and that's going to keep the pressure constant. So in Charles' law relationship, what happens is it's the volume that adjusts to allow the pressure to remain constant and have the same number of collisions when basically you adjust the temperature. Now, there is actually a gas law, which is known as Gay-Lussac's law, which is very similar to this one, which is P1 over T1 equals P2 over T2. This is at constant volume. And in this situation, when we increase the temperature, our volume doesn't change because it's constant. So we've got like a rigid container, and volume's not going to be able to change. It's just fixed. And because of that, the gas molecules will start to fly around faster, cause more collisions. More collisions will lead to an increase in pressure. So in this relationship, when the volume is fixed and you increase the temperature, you will actually start to see the pressure start to go up, because there's no getting around it. There's just going to be a lot more collisions happening, and that's going to cause a lot more pressure. Same thing will happen in this situation, if you lowered the temperature. If you lower the temperature, our gas molecule is going to move a lot slower. Dramatic drawing, a lot slower moving gas molecule. And that's going to cause a lot less collisions to occur. And when we have less collisions, we will actually see the pressure go down. So these are two laws which are kind of related to each other. Law of volume. And if you change the temperature, you will affect the pressure. And in Charles' law, the volume is not fixed. Actually adjusts to keep the pressure constant. Any questions on that there? So one of the interesting relationships that we see in Charles' law is if you make a plot of the volume versus the temperature, it will give you these straight lines. And if you take any of these gases straight lines and you extend their lines all the way back to the temperature, they all cross at the exact same point. They all cross at minus 273.15 degrees Celsius. Converted into Kelvin, we would add 273.15, and that is what is known as 0 Kelvin, or absolute zero, it used to be called, later named after Kelvin. So the result of that is, you could think that, I guess, that when you have any gas law ever, pretty much, the temperature always needs to be in Kelvin. So anytime you have a gas law that has a temperature aspect, like we do in both of these cases here, Charles' law and Gay-Lussac's law, they all have to be in Kelvin. So here, this is constant pressure. So the temperature needs to be in Kelvin. This temperature here needs to be in Kelvin. And it needs to be in Kelvin, and that really should be, when you're doing gas law, it's a no-brainer. Just that should be like the first thing you do. If you have temperature, just put it into Kelvin. Sometimes people do not do that because they come across a problem where they give you the temperature in Celsius and they ask for the answer in Celsius. So logically, people think, well, I could just leave it in Celsius because I want my answer in Celsius, and they gave it to me in Celsius. You cannot do that. You need to convert it from Celsius to Kelvin. You have to then put it into the gas law, and then after you get your answer, convert it from Kelvin back to Celsius. So whenever the temperature goes into the gas law, it has to be in that unit of Kelvin. Any questions on that there? No. All right, so let's try one here. An experiment. There's 452 milliliters of a gas used in a light bulb. It goes from 22 degrees Celsius to 187. What will be the final volume? So see what. Okay, so let's take a look. Now that we have a few sort of gas laws to choose from, we have our Boyles Law, we have our Charles Law, and we have our Gay-Lussac's Law. Once again, pulling out the information from the problem will help point you in the right direction if you're not sure. And again, we're just going to kind of pull out the information as it's written. So in an experiment, we have obviously a volume that is 452 milliliters. It is heated from a temperature of 22 degrees Celsius to another temperature of 187 degrees Celsius, and we're looking for a volume. So obviously, there's no temperature here, so that's eliminated, and there's no pressures here, so this one's eliminated. So it would be Charles' law that we want to use in this particular case. Here, like I said before, we do need to convert our temperature into Kelvin. So again, it's almost, if you got temperature, it should just be the first thing that you do when you're dealing with gas laws. So we're going to add a 273 to our 22, even though it looks like 220. And we've got a 295 Kelvin. Here, we'll also have the 273, and we got a 460 Kelvin there. And our volume is okay in terms of its units. And once again here, I'm just going to call my first set of information the ones, my second set the twos, and we're going to rearrange this equation here correctly, hopefully. And we are looking for V2. So that means that we need to move our T2 to the other side. So again, in this case, our T2 is on the bottom. which means when it goes to the other side, it will go to the opposite location, which is on top. And that means that we will end up with V1 T2 over T1 equals RV2. We're essentially multiplying the T2 to the other side, basically. Yeah, that's what we're doing there. Any questions on that there? Now that we did that, we want to also make sure that when we put our numbers in, we get our correct numbers in the right spot. So we are looking for V1 first, which is 452 milliliters. We actually want T2 on top. So that is our 460 divided by our T1, which is our 295 Kelvin. Here, the kelvins will cancel. That's going to leave us our volume in milliliters. So that's going to be a 452, maybe if my thing turns on, 452 times a 460 divided by a 295. That'll give us something like 705 milliliters as our volume. Again, in terms of Charles Law relationship, in this case, when we look at the temperature went up. That means in terms of the volume, we should also expect it to go up. It started at 452, it ends at 700 or so. So the volume did go in the correct relationship that we see with Charles Law. Question on that there? Yeah. For the final answer is actually in milliliters. The kelvins cancel out since there's two temperatures. Yeah, so these two temperatures here basically cancel out. And those two, what's that? Truthfully, probably we should round up on that, I guess. Since we did convert it to Kelvin at this point, these guys did technically end up at kind of three significant figures, although the 460, it depends on how you write that one. It could be 2 or 3. So 2 or 3 would be okay in this case. I didn't write the decimal there. So technically speaking, this would be 2 significant figures, which means this really should go up to like 710, right? Milliliters if we round it down. Question, yeah. You do. So it's a pretty much for sure thing. If you have a gas law, you have temperature converted to Kelvin. Even if your head tells you not to, because again, the problem says gives it to you in Celsius and wants the answer in Celsius, and it happens to a lot of people, they go, I don't need to do it. You need to do it. So you got to put it in the Kelvin, you have to put it into the equation and then convert it afterwards. So when you have that conversation later on in the semester, listen to the right answer to do. Any question on that? Well, we can't forget our friend Avogadro, right? He had a number. Why not a gas law? So Avogadro had a gas law. Avogadro's law, when we think about Avogadro's number, that is 6.022 times 10 to 23 atoms equals 1 what? Moles. Yeah, so it would make sense that his gas law involves moles. So Avogadro's law is V1 over N1 equals V2 over N2. And this is actually at constant pressure and temperature. N here is actually the moles. So in gas laws, N equals moles. And volume here is the volume. And the relationship that we see with Avogadro's law is basically as the volume increases, so does the moles of the gas. So they kind of increase proportionally and decrease proportionally as well. So that gas law, like all the other ones there, you could kind of use, plug and chug into it and solve for either volume or moles. And the reason I mentioned that one is when we take Avogadro's law along with Gay-Lussac's law, Charles' law, and Boyles' law, and put them all together, we do get the granddaddy of all gas laws, which is the ideal gas law there, which is our PV equals nRT. Now, PV equals nRT is the ideal gas law. It describes what's going on with an ideal gas. It's an ideal gas. It's pretty much every gas you deal with is an ideal gas because it makes the calculation easier. So we go, hey, that's an ideal gas right there. So under normal conditions, gases will behave ideally. And what that means is under normal conditions, there are two main things that make something sort of an ideal gas. One thing is, under normal conditions, the actual volume of the gas molecule itself is relatively small compared to the container is flying around it. And that's why if you look at a lot of gas law problems that you come across, they very often will talk about the volume of the container the gas is in rather than the volume of the gas molecule itself. And we think of an ideal situation that the volume of the gas is not that important versus the volume is flying around it. The second also important aspect that makes something an ideal gas is, in an ideal gas situation, you could have multiple gases in the same container, and we assume that there is like no interaction between those gases. So they're in there like ideally by themselves. You could almost think of them as being in that container by themselves. Even though they're flying around with other gas molecules, we assume that there is no attractive forces between the gas molecules. There's no repulsive forces between the gas molecules. And that's sort of the ideal behavior. So that's two things that make something an ideal gas. And that's ideally how a gas behaves under normal conditions of like normal room temperature and pressures that we deal with. Now, this gas law is PV equals nRT. This is also different than all the gas laws that we saw up to this point. Is not like a twofer. There's not two pressures, there's not two volumes, there's not two temperatures. There's a one and done situation here. One of everything is all we have going on here. It is also the most restrictive gas law in terms of units. So when you use the ideal gas law, the pressure has to be in units of atmospheres. It cannot be in any other unit. The volume has to be in pressure or units of liters. N, which is moles, should be in the units of moles. And just like every other gas law, our temperature has to be in Kelvin. The reason for all that is R. R is a gas constant. And it is a number that you always have available to you when you're doing gas law problems. Although they will never tell you that in a gas law problem. They'll never mention the gas constant or anything like that. That is one of those numbers that they just assume you know what it is and that you know you have it available to you. So when you read a problem, you'll never ever probably see the gas constant is this. They'll never ever tell you it. So that number, by the way, is 0.08206, and it has units of liters times atmospheres divided by Kelvin times mole. Nowadays, people like to round this number to 0.0821. I'm good with whichever number you want to use. I personally use the top number because that's the one they beat in my head and I can't get it out. So that's the number I use. But nowadays, books do round it a lot to 0.0821. So you can use either one you want. The nice thing about the gas constant, it'll probably be given to you, which means the units will be given to you, which means if you forget what any of these units are, they're sitting right there. So you could just know that they has to be in those units for everything to properly cancel out. So if you look at the gas constant units, that is the units that everybody else needs to be in there. Any questions on that there? Some other important information about the ideal gas law and relationships is this. Let's start with STP first. STP stands for standard temperature and pressure. And in a problem, if they say, what is whatever the volume at STP, they are actually giving you values for temperature and pressure when they say STP. The pressure is 1 atmosphere. The temperature is 273 Kelvin. So when they say in the problem at STP, those are the actual values that you could use for pressure and temperature and put them into something like the ideal gas law if you wanted to use it there, or any other gas law, by the way, if you happen to use it. Now, there is a really kind of nice relationship that if you are at STP conditions, and you happen to be at STP conditions, 1 mole of any gas will have a volume of 22.414 liters. That is a conversion factor that if you happen to be at STP, you could use, and you might not have to use the ideal gas law. So you could kind of bypass the ideal gas law and use that as a conversion factor. But it definitely has to be at STP. So if the temperature is not 273, the pressure is not 1 atmosphere, you should never use that conversion. If you don't want to worry about using that conversion incorrectly, which might be a good idea, you could always use the ideal gas law in every situation. Even at STP conditions, non-STP conditions, you could just throw everything into the ideal gas law and you'll be fine. So you don't have to worry about that conversion if you don't want to. You can throw the pressure and temperature into the ideal gas law and it'll come out the same. So that's why we use the ideal gas law. It really is like a universal gas law. It works pretty much for everybody under all conditions. You could use that gas law. By the way, if we solve for R in the ideal gas law and we put in all of our values at STP, that is how we get the gas constant. That 0.08206 number comes from basically solving for R with all of our STP conditions. Any questions on that there? All right, let's try one here. Calculate the pressure in atmospheres exerted by 1.82 moles of SF6 gas in a steel container that has a volume of 5.4 liters and 69.5 degrees Celsius. These are formulas that we learned. We got this one here, Boyles. We got Charles. We got Gay-Lussac. Got our friend Avogadro. And then we have our ideal gas law. So we take kind of the same approach here. We're looking for the pressure exerted by that many moles, 1.82. And we have a volume of 5.43 liters and a temperature of 69.5 degrees Celsius. Again, we pretty much have one of everything, which eliminates all these equations and points us in the direction of PV equals nRT. You can kind of see it. Remember, just like this problem, they never mention the gas constant, but that is a value you always have, or a number you always have available to you. So we are going to use the ideal gas law here. Our units of volume is good. It's in liters. Our temperature is not good. So like normal, we're just going to add our 273 and convert it to Kelvin. And looks like a 342.5 Kelvin. And everything else is good. Moles are in moles. By the way, also very common in gas law problems is you're not given moles, but you're given grams. So kind of like we did before, that grams to mole conversion is used a lot in gas law problems, using the molar mass to do that. Also, a lot of times you're given volume in milliliters, and going milliliters to liters is also a very common conversion that you sometimes need to use. Again, 1,000 milliliters is equal to 1 liter. So those are two common conversions that you sometimes have to use here. PV equals nRT. We're going to solve for P, which again, everything's on top, which means when the volume goes to the other side, it's going to go onto the bottom. We're going to divide it to the other side. And pressure would equal nRT divided by V. And putting in our numbers here, we have our 1.82 moles. We have our gas constant, liters, atmosphere, Kelvin, mole. We have our temperature that's been converted to Kelvin, all divided by our volume, which was in liters to begin with, which is good. That means that the moles and the moles will cancel, the Kelvin and the Kelvin will cancel, the liters and the liters will cancel. That will leave me just atmospheres left over, and that's good because that's a unit of pressure. And we go 1.82, I guess it's the right number, 1.82 times 0.08206 times 342.5 divided by 5.43. Going to yield me a 9.42 atmospheres as our pressure in this case. Questions on that one there? So again, common variations on ideal gas laws, those other conversions you have to do, grams to moles using the molar mass, just like we did in the previous chapter, and also that milliliter to liter conversion, also a very common one. Any questions on that there? Yeah.
This one specifically, we have to use the PV NRT formula.
We do, because
Any questions for the other formulas specifically?
yeah, so like we did some examples earlier, we used those guys. Yeah. Yeah. Other questions? All right. Now you can look at changes in all three variables, pressure, volume, and temperature. And if we set the ideal gas law equal to each other in two different sort of situations, we get another gas law, which is a really important gas law, which is sometimes referred to as the combined gas law. And that is P1 V1 over T1 equals P2 V2 over T2. Here again, the temperature does need to be in Kelvin. The pressure on both sides just needs to be the same unit. It can be any unit you want. Volume needs to be the same unit on either side. It could be any unit as long as they're the same. We also will usually have the same number of moles on each side, and that's how the moles sort of go away. Why this equation is the one that you should invest your time in remembering is because of this. If you take this equation, and if you want, that is P1 V1 over, if you want to leave the moles in there, you can, N1 T1 equals P2 V2 N2 T2. If you remember this equation and only invest your time into this equation, along with the ideal gas law, you can pretty much get every other equation from it. So for example, if I come across a problem and the only thing I see is pressure and volume in the problem, no temperature, no moles mentioned, or they say they're constant, I just scratch it out and there's Boyles Law. Yeah. If I take this equation and I come across a problem where I see nothing about pressure or moles, I scratch them out on both sides. There's Charles' law. If I take this equation and I come across a problem where I do not see anything about volume or moles, or they say they are constant, I scratch out the volume and the moles on each side. And there's Gay-Lussac's law. And as you could probably get the hint at this point, if I come across a problem and it mentions nothing about pressure or temperature, or they're constant, I just scratch them out. And now I have Avogadro's law. That's all the other laws we just talked about, right? So all you have to do is remember that law, scratch out whatever's not mentioned, whatever is constant, and you'll have the right gas law that you need to use. So if you remember this gas law, which is the combined gas law with the moles or without the moles, however you want to do it, and you remember PV equals nRT, you'll have every gas law you need at the palm of your hand just from those two equations. You'll be able to solve everything that you need by just remembering those two equations. Any questions on that? All right, it was worth waiting the extra 2 minutes for that, I think.